Right. So probability. Like this is one of the most like easiest questions you will get in your O-level paper. Right? There's no need of much theory. It's just pure logic, not even mathematics. It's pure logic and a little bit of math, like so fractions and stuff, multiplication and stuff. Right? So let's see. There's no much deep basics in probability. You just have to know two words. Random experiment, and the other is sample space. So if you guys know these two, we can proceed to the questions. Let me explain what a random experiment is. A random experiment is an event where you know all the outcomes. You know all possible outcomes. For example, let me know the outcomes. Let me know the results. If you toss a coin in the air, what would be the results? There's only two outcomes, right? Yeah, one would be heads and the other would be tails, right? So heads or tails. You know all the possible outcomes, but can you exactly say which outcome you will get? You can't exactly say, right? So that's the definition of a random experiment. Can't exactly say. Like, you know all the possible outcomes, but you can't say the exact outcome, right? So if I give you an example, rolling a dice. If you roll a dice, would that be a random experiment? Rolling a dice, would it be a random experiment? Yes, right? Yeah. Because like you know all the outcomes. What would be the outcomes? 1 to 6. A die has 6 sides, 6 faces. So you will get 1 to 6 as the outcomes, but you cannot say exactly which number you will get. Right? That's a random experiment. And like the sun rising in the east, is it random? The sun rising in the east. No, that's not random. That's definite, right? That's definite. What's the possibility? What's the probability of the sun rising in the east? The probability is 100%. Whereas we can say in numbers, the probability is 1, right? This is clear. The sun definitely rises in the east. So the probability is 100%. You have a pack of cards, you know, pack of cards, right? So you have a pack of cards, and when you choose a card, you will get the card 7 of hearts. Like there are many cards, right? So is this random? Like you have a deck of cards and you choose one card and that being 7 of hearts. Is that random? Yes, right. That's definitely random. Because there's a lot of cards, around 54. So one card out of this would be random. That's definitely random. You know all the outcomes, but you cannot exactly say if you will get 7 of hearts. So that's random. So is that clear what a random experiment is? Yes, good. And in the exam, they always mention this word random because to indicate that you are dealing with a random experiment. So that's it for random experiments. Like that's just basic stuff. You know all the outcomes, but you cannot say exactly which outcome you will get. So that's random experiment. And the meaning of the sample space is the sample space is simply all the outcomes. The sample space is all the possible outcomes. The sample space is denoted by S, the letter S. Right? For example, if I ask the sample space of tossing a coin, what would be the sample space of tossing a coin? the sample space of tossing a coin would be heads, tails. This is the sample space. And if I ask you the cardinality, I mean, if I ask you the number of elements in the sample space, that would be 2, right? The number of elements in the sample space is 2. And the sample space is heads or tails. Okay. So this is simply sample space. If I choose a dice, the sample space would be 1, 2, 3, 4, 5, 6. And the number of elements in the sample space would be 6. So this is it for sample space and random experiment. Did you guys understand these two? Like, there's nothing to understand. You already know, right? I just reminded you guys. Right. So this is sample space and random experiment. So we can write the probability of any event. Like, I'll name this event A. If you need to get the probability of event A, you need to know the number of outcomes, the number of possible outcomes in A, and divide it by the number of elements in the sample space. Like, you don't have to understand this. Let's see an example. I have a dice, and I need the probability of getting an odd number when I roll the die. The probability of getting an odd number. So I'll mark it probability of getting an odd number, PO. And let me know how many odd numbers are there in the dice. How many odd numbers? There's 3 odd numbers, right? 1, 3, and 5. There's 3 odd numbers. So number of outcomes is 3. That's NA. And how many elements are there in the sample space in a dice? 6. Yes. So the probability of is simply 3 out of 6, or else it's 1 out of 2. Right? You guys learned this since grade 9, grade 9, 10, and also in 11, I guess. You guys learned. Right. So let me know in the same dice. Let me know the probability of getting a square number. 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 How many square numbers are there in the dice? 1 is a square number and 4 is a square number, right? 1 and 4 are the only square numbers. The first square number is 1 and 2 squared is 4. 3 squared is 9. So you don't have 9 here. There's only 2 square numbers. So we can mark the probability as 2 square numbers out of the total numbers. 2 out of 6 or else 1 out of 3. Is this clear? Yes, okay. So if you have just one experiment going, like you do the experiment once, so you can easily take the probability by this formula if you do the experiment only once. But if you are doing it twice in your syllabus, the maximum times you can do an experiment is twice in your syllabus, right? So if you do it twice, you will have to go for something called graphical representation. So that's where your O-level exam paper comes in. Right? In the graphical representation, there's 2 types of representations. One is the probability grid. One is the grid, and the next one is the tree diagram. So, like these two, NA means the number of possible outcomes of this event A. Like, if A is the event of getting a square number here, the number of possible square numbers, the number of square numbers is 2. So NA is 2. Is that correct? Okay. So, like I said, grid and tree, these are the two things they are going to test in the exam. So you need to know these two very well. Right? Let's see, the grid is something like this. You guys have possibly seen a grid. The grid has two number lines on it and all the same outcomes. For example, I'll take an example. You have a box, and in that box, there are, let me use the color. There are two red marbles. There are two red marbles and three blue marbles. Correct? There are, yeah, like a graph, like the positive axis only. Yeah. So there are two red marbles and three blue marbles. So listen to the story. Two red marbles and three blue marbles. And someone, like there are two people. One is A and B. This guy is A and he is B. A and B are there. So A puts his hand, takes out a marble. A puts his hand randomly and takes out a marble and notes the color. Like he records the color somewhere and then puts the marble back inside. And then what happens? B puts his hand and takes out another marble, records it and puts it back. Is the story understood? Let me know how many times this experiment is repeated. Twice, right? Yeah. A maximum of 2 times it can be repeated. So it's repeated twice. I'll take this number line, this axis to be A's axis. This one. And I'll take this to be B's term. Right? So they ask us to mark the sample space. So I told you what the sample space is. Sample space means all the outcomes, all the possible outcomes. So I'll have to mark all the outcomes. So they also give you these coordinates, like these stuff. This should be like there are 3 blue marbles, right? I'll mark this as B1, B2, and B3. The reason I have 3 blue marbles, so that's B1, B2, and B3. And what else do we have? R1 and R2. Is this clear? The way I mark in the exam, they'll be giving this, right? The exam they'll be giving this. So A's turn and B's turn also, they are the same things. B1, B2, B3, and R1, and then R2. So these are the only possible stuff. So when marking in the grid is something like this. It consists of dotted lines. And see, this is A's turn, this is B's turn. So I have to mark the sample space. Generally, they are giving us this mark, the cross. We have to mark the sample space by crosses. So if I say, like in A's turn, he got the first blue marble, B1. Can B also get this first blue marble in his turn? Like A puts his hand, takes the B1 and puts it back. Is there a chance for B to get the B1 marble? Is there a chance? There's a chance, right? Because A takes the marble and also puts it back in. So the B1 marble is still in the box. So B has a chance. So that's the outcome. So likewise, everything is possible, right? Is this understood? Like A getting B2, if I choose this cross, this means A gets B2 and B gets R1. Is that clear? A gets B2 and B gets R1. Is it clear? This is how we mark. Yeah. So R2 here, like this. So you will definitely be doing this in the exam, and for doing this you will get marks just for marking crosses on a grid. I can imagine they give you marks for marking crosses on a grid. Maths, all elements. So this is the first step. You mark the sample space, like all the possible outcomes, and then they ask you to do something like they ask you to circle the probability of both people getting red marbles. They will give the grid. They definitely give the grid. You don't have to like mark it. You don't have to create the grid. So they ask you to circle the probability of both A and B, both guys getting red marbles. Both of them must get red marble. So what is it? See, this is A's turn. So A getting red is this. A getting red. Right? But B also must get red. B also must get red. So do you understand that this is the probability? This is the sample space of that. This is the event space. Like A must get red and also B. B cannot get blue. So A must get red and B also must red. Is it clear how I mark? Both gets red. Yes, good. So, and they say to find out the probability. So the probability is simply the number of outcomes in the event, that's 4, divided by the number of elements in the sample space. How many crosses are there in the sample space? How many crosses are there in the sample space? That's 5 times 5, 25. Yes. So the probability of both of them getting red marbles is 4 out of 25. Is this clear? Okay, now you guys let me know the probability of both getting blue marbles, both of them getting blue marbles. What would be the probability? We can't further simplify this, right? We can't cancel these. If you can, then you can. Like if it's divisible by some number, you can make it the simplest way. Yeah. So the probability of both getting blue is 9 out of 25, right? Because see, A must get blue and also B. So both guys must get blue marbles. So this is the probability. So there are 9 crosses. The probability would be 9 over 20. Right. Answer this. What's the probability of at least one of them getting blue? Like both of them, that's not necessary. If at least one person gets blue, that's enough. What's the probability? At least one of them getting blue. At least one. I'm getting answers, but those aren't correct, I guess. So this is where they tackle you in the exam. At least one. So if they say at least one, it can either be A or B. It doesn't matter. Like A can get blue, A can get blue while B gets red. Is that clear? Because at least one. Adu can I? Like they need only one person to get blue. So if A gets blue, that's perfectly alright. B gets red, that doesn't matter. But if we see in B's perspective, he must get blue, and the color of A is like not necessary. It's like this, right? Like check the crosses. If you check this cross, B has got blue, and A has got blue, and B has got red. That doesn't matter. Yeah. So this is the only thing you cannot color because here both guys get red. Here both guys get red. Here too. Here and here. So this cannot be colored. So if they say at least, it's enough if one person gets blue. So you can color the union. You can color the union of both. You can color this and this. Is that clear? Yeah, now I am receiving correct answer. I'll repeat. Like, give me a sec. If they say at least one person gets blue, Can both people get red color? They say at least one must get blue. So can both people get red color? Think the other way. So both people cannot get red color. So you can't color this. Both people cannot get red color. So you can't color this, but you can color any other thing. Because anywhere else, at least one person gets blue. See this? In according to this cross, what's the color of A? What's the color of the marble A gets? See A's turn. This is A's turn. According to this cross, A gets blue color. And according to this cross, B gets red color. Yeah, B gets red. That doesn't matter because one person, at least one person, has got blue color. Simply, if they say at least one person gets blue color, we cannot color both people getting red. Is that clear? Like both people cannot get red. Right? See, if one person needs to get blue color, how come if both of them get red color, who will get the blue color? That's simple logic, right? You can't let them both get red color. You'll just have to color circle the other stuff. Okay. So this is where they test you in the exam. There's an exact question like this. Let's try it after we finish May grades. Okay. Is the circling process understood? Let's imagine, for example, these are not marbles. For example, these are candies, toffees or something, right? So A puts his hand, takes a toffee and eats it. And then B puts his hand and takes the toffee and eats it. Right? So can this exist now? Can this cross exist? Because see, if A took B1, like if A chose B1, he eats it, right? If A eats B1, can this guy get B1? So this cannot exist neither. What else cannot exist? B2 cannot exist because A eats B2, this guy doesn't get B2. So likewise, all these crosses in the diagonal, like in this diagonal, the crosses cannot exist. If somebody eats it or somebody throws it away, there's no two times for that. Is that clear? What I erased? A puts his hand. If the topic is B1, this guy cannot have B1. B puts, again, if the topic is B2, this guy cannot have B2. All the other processes can exist because he eats B1 and this guy eats B2 here. So that doesn't matter. Yeah, that's clear, right? So now let me know the probability of both of them getting red color. Now let me know the probability of both of them getting a red color topic. Yeah. Consider the denominator also, like it's 2, yes, it's 2, but is it out of 25 now? No, we erased 5 of them. So it must be 2 out of 20, right? It must be 2 out of 20 or else 1 out of 10. The denominator also changes. What's the probability of both of them getting blue color? Both of them getting blue color is 6 out of 20 or else 3 out of 10, right? Yeah. So I have to circle this name. So this that's 6 out of 20, or else 3 out of 10. Yeah. So are probability grids clear? Those are the only two things. Sometimes the sample space exists everywhere, or else the diagonal gets erased. In your O levels, the diagonals. No, it's not compulsory to put the answer in the simplest form in probability. In probability, even if you keep this as 2 out of 20, you will get full marks. Right? You don't have to simplify. It's not necessary. In the O-level question, they definitely give you like this diagonal. It doesn't exist. Such questions are given in O-levels. Let's see. Okay. So if we are good with grids, let's move on to tree diagrams. The same example I'm choosing for tree diagrams. See how much? 2 red, right? 2 red marbles and 3 blue marbles. 3. In the tree diagram, we denote one turn by one tree. So this is A's turn. Suppose he picks red or else blue. So if he picks red, B gets a turn, right? If he picks red, B gets a turn. Even if he picks blue, even then B gets a turn. So this can be red, blue. So is that understood why the branches are diverging? Because if he chooses red, then there's a tree. If he chooses blue, there's also a tree because B definitely gets a turn. This is clear. Right. So in tree diagrams, we denote the probabilities as fractions, mostly as fractions. Right. So there are two red marbles. So that must be 2 out of 3. Sorry, 2 out of 5. Altogether, there are 5 marbles altogether. That's the sample space. So this is the probability of red. Let me know the probability of blue branch, this branch. What's the probability? 3 out of 5. So there's also a method to find this even if you don't have the data. The method is the sums of these two branches, like 2 out of 5 plus the answer must always be equal to 1. Again, if here's 2, here definitely must be 3. For example, if here's 7 out of 10, what would be here? In order to it to be 1, what would be here? Yeah, that must be 3 out of 10. Because the sum is 10 out of 10, right? 7 plus 3, 10 out of 10, that's 1. If there's 2 out of 7, what would be here? 5 out of 7. So that's clear. You don't have to have all the data. If you just have the data on one branch, you can find the probability of the other. So consider this. This is not candies, not toffees, just marbles. So they see the marble, they record the color, and they put it back in. So when going to B's turn, does the number of marbles change if they put it back in? No, right? It doesn't change. So here also red color must be 2 out of 5 and blue must be 3 out of 5. Here it's 2 out of 5 and 3 out of 5 because there's no change. So is this clear how I mark the probabilities? Yeah. And in the exam, they don't ask you to do this, but it's a good practice. If you do this, it's you name these branches. See, it's red, red. The next branch is red, blue. This branch is blue, red. And this branch is blue, blue. Now, you can also find the value of the RR branch. That's 2 out of 5 into 2 out of 5. That would be 4 out of 25. Is it clear how I got the value? Okay, let me know the values of these 3 branches quickly. No, I can't lend you my brain. I'm sorry. You guys have exams, right? Going on. So this is 6 out of 25. 6 out of 25. 9 out of 25. Good. Yes. Yeah. I'm receiving answers. Great. Okay. So now you have everything you need to answer the question. So if you see this probability question in O levels, just do this. Mark the branches, fill the branches, and also do this. Label the branches and take the value. So whatever the question they ask, you can answer. So let me know by looking at this, the probability of both marbles being red color. What's the probability of both marbles being red color? Yes, both marbles being red color is R, right? Red, red. Both being red. So what is it? It's 4 over 25. Okay, what's the probability of both marbles being blue color? Yes, it's B. 9 out of 25. 9 out of 25. Good. So, like that's simple, it's both red, both blue. Let me know the probability, like listen carefully, the probability of exactly one marble being red color. The probability of exactly one marble. Like both cannot be red, right? Exactly one marble must be red color. Yeah, if they say exactly one, how many branches you have? Where exactly one marble is red color. See, here exactly one is red color. Here too exactly one is red color. So you must add these two. That's 12 over 25. Exactly one. Right? You got two chances. So you must add up those. That's clear, right? So now let me know the final thing. At least one marble, at least one. Right? Keep in mind the word at least. At least one marble being blue color. At least one must be blue. What's the probability of at least one being blue? I see mistakes. Yeah, that's correct. So at least one. So there can be two blue colors. That doesn't matter. At least one must be blue. Here at least one is blue. Here one is blue. Here neither of them are blue. Here at least one is blue, right? So you must add these three. 6 out of 25 plus 6 out of 25 plus 9 out of 25. That's 21 out of 25. Is that clear? Yes. And always remember, you always get proper fractions for answers. Proper fractions, not improper ones. Proper, because if you receive a unit fraction, like this is the highest probability of something occurring, that's 100%. Right? You cannot receive something more than one for an answer. You always get proper fractions. For like if you do something and you get 27 or 25, please note that your answer is wrong. Try that again. Right? In the exam, if you get something like more than the denominator, something the numerator is higher than the denominator, then your answer is incorrect. Right? Keep that in mind. So I guess we are okay with three diagrams, but there's another small thing we have to do. Right? That is the candy scene. Like this is a marbles neck. If we go with candies, like with toffees, what happens? See, this guy gets red color. Like there's 5 toffees. 1, 2, 3, 4, 5 toffees. Alright. So in the end of A's turn, he definitely eats 1 toffee, right? Yeah, he definitely eats 1 toffee. So how many toffees would be remaining here? That must be 4. In every branch, now the number of toffees is 4. In the denominator, there must be 4. Is that clear? Because no matter if it's A or like no matter it's red or blue, he eats it, right? He eats 1 toffee. So no matter the color, the denominator changes. It decreases by 1. He eats 1 toffee. All right. Now, see, there were 2 red toffees, and this branch is red. So what color toffee does he eat here? He eats a red toffee. So how many red toffees are now remaining? 1, exactly. Like in this instance, he eats 1 red toffee. So there's 1 red toffee remaining, and there's no change done to blue toffees. So that's 3. Even if you don't get this, like if it's 1 out of 4, the remainder must be 3 out of 4, right? Is this clear? How the 2 became 1? Because he eats 1 red toffee here. Yes, okay. So let me know the numerator here. What would be the numerator? Here, 2, right? Because see, he eats a blue toffee. He eats a blue toffee now. So it doesn't change the number of red toffees. The red toffee number is now 2. That doesn't change. But how many blue toffees are there now? That is also 2 because there were 3, but he ate a blue toffee. So it is 2 out of 4. Like in here, he eats a red toffee, therefore it changes. But if this thing happens, these are 2 instances. Both cannot happen at once. If this happens, a red toffee gets decreased. If this happens, a blue toffee gets decreased. Is that clear? Yeah. Both cannot happen simultaneously. This is a branch of possibilities. Good. So I'm not gonna ask questions from this slide. You know, right? What to do? You must name the branches and put the results, and then you can answer any question from it. Right. So let's go to the O-level questions. 2018, I guess. Yes, 2018. We have only around 15 minutes remaining. So let's read together and do it. Like I'm not gonna give you time separately. You can read it with me till I put the grid. You read the question and let's do it. So this is the grid. Now see a bag. Let me check what's up division. I didn't receive it yet, I guess. Let's see. The bag contains 3 vanilla flavored milk packets and 2 chocolate flavored milk packets of the same size. After Kamala takes out a milk packet randomly, Nimala also takes out a milk packet randomly. So this is Kamala and this is Nimala. Let me know if they put back the milk packet. Have they mentioned about something about putting back? No, they do not put back the milk packet. So the diagonal cannot exist. So let's mark the sample space. I guess everyone is good at marking sample space now because the diagonal cannot exist. So this would be like this. This. Is this clear? How I marked it? Yeah. So they don't put back the paper. So in O levels, like it's a tradition, they always give you the diagonal like in such a way that the diagonal is missing. So for the Roman number 1, that's it. You will just have to mark the sample space. If you mark this also, then you won't get marks, correct? Okay. In the grid, calculate, encircle the event of both of them taking out vanilla. That's pretty easy, right? Encircle it and find out the probability and let me know. Let me know the answer. Yeah, I'm receiving answers. So let me encircle that both must get vanilla. Yes, both must get vanilla. So that is this both getting vanilla. Right? So it's 6 out of, it's not 25 now. We erased 5. That's 20. 6 out of 20 or else 3 out of 10. Both answers will get you full marks. Right? 6 out of 20 or else 2 out of 10. Right? Sorry, 3 out of 10. And then there's a tree diagram. Read it. I'll draw the tree diagram. So they say the probability of a certain sports team winning the first game is 3 out of 5. So that's also mentioned, like it's even marked in the question. We don't need that, like we can mark this as 3 out of 5 because given in the paragraph, the probability of them winning the first game is 3 out of 5. So let me know the probability of them losing the first game. What is it? Yeah, exactly. That's 2 out of 5. Because it's 3 out of 5, definitely the remainder must be 1 minus this. Right? 2 out of. And then they say if they win the first game, like if they win, they are talking about this tree now, the upper tree. If they win the first game, the probability of them winning the second game is 7 out of 10. Let me know the probability of them losing the second game. 3 out of 10. 3 out of 10. And they say if they lose the first game, the probability of them winning is half, 1 out of 2. So what would be the probability of them losing the game? It's also, yeah, so it's 1 out of 2. So it definitely must be 1 out of 2. 50-50, right? Half. Is this clear how I mark? So that, yeah, that's the answer for Roman number 1. Like we must mark all the possible outcomes. In the grid, we mark crosses, and in the tree diagram, we mark fractions. Right? Now they ask us the probability of the team winning at least one game. So you guys calculate it and let me know the answer. Winning at least one game. I'll just name the branches. WW, LW, L. Yeah, I've received answers like winning at least one game, right? So let me know what, like I'll mark these 1, 2, 3, and 4. Which numbers should I add? Winning at least one game. There must be at least one W here. So what are the things I should add? The first one, I must add the first one, right? Because there's at least one W here. And the second one and the third one. Yeah. I must add all these except 4. Correct? Is that clear? To win at least one game, I must add all these 3. Correct. So this is 21 out of 50 plus 9 out of 50 plus 1 out of 5 is 10 out of 50, right? If I multiply this by 10 to make the denominators equal, it's 10 out of 50. 21 plus 9 is 30 plus 10 is 40. 40 out of 50. Divide both by 10, you get 4 out of 5. This is also acceptable as well as this. Is this clear? Yeah. Okay. I'll answer the second one again. See, they ask us to find the probability of team winning at least one game. So there must be at least one W, right? These are the 2 games, at least one W. So I must add this, I must add this, and also this. I can't add this because there's no W here. So I just have to add these 3. Those are fractions. So 21 out of 50 plus 9 out of 50. This is 1 out of 5. In order to make the denominator 50, I multiplied both by 10. So that's 10 out of 50. Let's add these. 21 plus 9 is 30. 30 plus 10 is 40. 40 out of 50. I hope it's clear now. Let's do the 2017 question quickly. And then let's wind up the session. Try reading the 2017 one and send me the answers. I'll draw the grid and catch up. All right, let's see. The box contains 5 bulbs which are identical in shape and size. Of these, 2 are burnt out. So 2 bulbs are burnt and the rest are good bulbs. Right? 2 burnt bulbs and 3 good bulbs. Using a bulb is drawn randomly from the box. See, they use the word random to indicate the experiment is random. From the box and examine and without replacing. Like, what does without replacing means? Do they put it back in or out? Without replacing. They do not put it back in, right? Yeah, they put it out. They don't replace, they put it out. Right? Without replacing. So definitely this diagonal cannot exist. So we don't even have to read the rest of the question. We know what to do. We just have to cross this. So that's the answer for Roman number 1. And they say encircle the event of drawing at least one burnt out bulb. At least one burnt out bulb. Okay. Let me know the answer for that. At least one burnt out. At least one. So keep the keyword in mind, at least one. So there must be at least one burnt out. There cannot be all good bulbs. So you can't circle this thing. Do you understand? If there must be at least one burnt out, the both bulbs cannot be good. So this ring, this circle cannot be circled. Like this cannot be circled. So you must circle the rest, right? The rest, at least one burnt out. Is this clear? So what's the probability of this? So 8 plus 6, it's 14, right? 14 over 20. The probability is 14 over 20 or else 7 over 10. Is this correct? Like, is this understood? 7 over 10. At least one. Okay. So the keyword is always at least or else exactly. If they say exactly one, you can't color this. Exactly one. So sorry, like both the bulbs. If they say both the bulbs are burnt out, you must color this thing. You must circle this thing. Both burnt out. If they say at least, that is this. What you did just right now. Now moving on to the tree diagram. I'll draw the tree diagram. This is the first row and the second row. Like the tree diagram is like it's continuous, right? So the same scenario about bulbs, it continues. Let's see. An incomplete tree diagram relevant to the experiment is given. Complete the tree diagram by indicating the corresponding probabilities. A burnt out bulb is denoted by B and a good bulb by G. So this is burnt out, good, burnt out. So there are like we know there are 3 good bulbs and 2 burnt out. So what's the probability here? 2 over, so that's 2 over 5. 2 over 5, and you can mark the denominators here now, because we know no matter what the bulb is, they are gonna put out one bulb. They are gonna throw out one bulb. So what would be the denominator in every branch? What's the denominator? Is it 5? No, it's not 5 because there were 5 bulbs, but they remove one. Like 3 good bulbs and 2 bad. They remove one definitely, so the denominator is 4, right? Is it clear? Yeah, good. Now, let's see if this guy, like, what bulb does he remove now here? In this instance, it's a good bulb. It's kind of a tongue twister. Good bulb. Okay, good bulb. So one good bulb is removed. So how many good bulbs are remaining? 2. Yes, that's 2. So if you know the numerator here, you can easily put the numerator without hesitation. It's definitely 2. So there's 2 bad bulbs. He puts out one bad here. So how many bad bulbs here? The number of bad bulbs now, he puts out 1. So the number of bad bulbs is 1 out of 4. Is that clear? Because there were 2, he puts out 1 bad. So bad bulbs are 1 out of 4. He doesn't change the good bulbs because he chooses bad here. So the number of good bulbs must be 3 out of 4. Are we clear? Are we clear? So it's just a matter of logic and understanding. No maths here, like you just have to write numbers. Okay. So mark the branches and answer the final question. Send me the answer for the final question. They ask us the probability that exactly one. Let's see, exactly 1 bulb must be burned out. Exactly 1. Let's see who answers correctly. I'm receiving answers. Good. Yeah, I have received 2 correct answers. Great. Exactly 1 must be burnt out. Okay, I'll mark the values here. 6 out of 20. This is also 6 out of 20. 6 out of 20. 2 out of 20. What about the others? I just got 2 answers, correct ones. Okay, they say exactly 1, right? Exactly 1 bulb must be burnt out. Let's see. Just look at the letters. Can we include this? Exactly 1 must be burnt out. Exactly 1. Can we include the first one? No, we can. We can't include this. Can we include the second one? Yes, exactly 1 is burnt out. Can we include the third one? Yeah, we can include that because exactly 1 is burnt out. Let me know if we can include the fourth one or not. Can we? Can we include the fourth one? No, we cannot. Why is that? Because they mention the word. They say exactly 1 must be burnt out. How many are burnt out here? 2. So this cannot be included. Comprehension, right? You must interpret the scenario properly. Exactly 1. So this cannot be included and this cannot be included. Both these can be included. So add these two. 6 plus 6 is 12. So the answer will be 12 out of 20, which is 6 out of 10, or else 3 out of 5. Any of these answers are acceptable. Is that clear? Yes. If you have doubts, you can ask. So always look for the keywords. The keywords, like mostly that's at least, exactly, both. These are the keywords. So look out for this. This is where you make mistakes. In the previous example, we did at least one game. In the previous question, we did at least. At least and exactly are 2 different things. So if they say at least 1 bulb is burnt out, you can also check me at this, because at least 1. The minimum is 1. Maximum is not defined. It can be 2. At least 1 bulb must be burnt out. Right? If they say exactly 1 must be burnt out. 2 can't be. Exactly 1. Is that clear? The keywords. Right. Right? Yeah, good. So that's it for today. I guess we are good. Okay with probability. You will just have to practice more questions. So I hope you guys don't need another session for probability. Correct? Let me know in the group. I'll put up a poll. So yeah, whatever. Let's end the session for today. God bless.